Okay, today we changed topic slightly. So last few lectures we talked about fine dimensional representations, and today we will talk about another class of representations, affine quantum groups, which has relation to Schur-Weil duality, and at the end with semi-infinite construction, whatever it means. Let me start with a few remarks about what is standard Schur-Weil duality. I can call it classical, but it doesn't mean that it means we have some Poisson meaning. It means that classical is well known. This is what actually what Schur-Weil did. And classical fact is the following: so we can consider the following vector space: Cn times Cn times Cn, whereas the number of factors is n capital, and there is the action of two different groups on this space or algebra. So on one hand, there is an action of the group GLN. On algebraic level, we will talk about universal enveloping of the Lie algebra GLN. On the other hand, we can permute factors, so there is the action of the permutation group S n capital, or if you want, the action of the its group algebra. So we have there is the action of two of these two groups of two algebras, and the standard theorem these two actions commute and the whole space Cn capital is a direct sum of say V lambda times R lambda, whereas this factor is irreducible representation of GLN, and this is reducible representation of Sn. And I don't recall this how the representations of GLN and Sn are labeled by partitions. And what kind of partition do we have here? But all V lambdas are different and all R lambdas are different. So in particular, this decomposition implies that these algebras are centralizers of each other. They're mutual centralizers. Centralizers of image GLN of your GLN in endomorphisms of Cn tensor n is image of the group algebra, and vice versa. This could be viewed as a part of the theorem, or it is follows from the, this actually follows from the decomposition. On the practical, another way you can say that this vector space is a bimodal. It has two structures. For example, using it, you can construct functor from the representation of GLN to the representation of SL, and this functor is the equivalence between certain subcategories. Are there any questions? Should I repeat something, or do you hear some noise due to some problem? I don't know who's working near me, but you can see some noise. You can hear some.
No noise.
Okay. What happens in Q-deformed situation? If we have for any representation of the quantum group, we are talking only we deal only with type A today, representation V. We have a matrix which permute two actions, two coproducts, delta and delta opposite. As usual, we can multiply this R matrix by permutation, obtain R tilde, and this R tilde now permutes. If we had two different representations, it will map from V tensor W to W tensor V. Now it will be mapped from V tensor V to V tensor V. Maybe I should write it, not just same words. So this separator, we checks from V tensor V to V tensor V with the same coproduct. So we obtain some operator which commutes with our algebra, which is now quantum group. And Young-Baxter equation in terms of R tilde has the following form. This part was quite generic, but now we can take for V, we can take as above, we can take Cn, tautological representation. First fundamental representation, whatever it means. And computer matrix. I'm not going to do this computation. For SL2 case, this fact was stated sometime in my last year course. For SL3, this was a problem from the very first lecture, that if you take universal matrix and compute it for this representation, you get something like this. And it is, I hope, easy to see that this is just a generalization of the same formulas here. So for and based on these two, it is quite easy to get the general answer. We have some prefactor here. It was q in power minus 1/3, q in power minus 1/2. So in general, it will be q in power 1 over n, and then we get this sum. This prefactor, in principle, I can even ignore it from the very beginning, because when I said that a matrix is intertwiner, this doesn't fix its normalization. In principle, if these representations are somehow very difficult, then it can be many intertwiners. And actually, even in this case, there are many intertwiners. But there is the standard choice. We take universal R matrix, and then compute it on these representations. If we do proceed like this, we get some root, some factor like this, and I absorb it on the left side. and this operator isn't intertwined. This constant doesn't change the intertwiner property, and also it doesn't change the this Young-Baxter property. Sorry, it is as it's written, it is not Young-Baxter property, just an identity, but I can make it Young-Baxter. So this is a so this operator which commutes with quantum. And what kind of algebra do we get? We get the Hecke algebra. Let me define it. Definition: the Hecke algebra is the Hecke algebras are assigned to the while groups. So in this now we the Hecke algebra which we are compute, it's for you can write for while group. For in terms of root system, it is an-1, or if you want this in some sense, it is SLN. Yes, here it is SLN. Okay, for SLN, it is an algebra which is generated by I plan to state this theorem, but no, is generated by generators T1, Tn-1, such that which satisfies the following relations. Okay, with relations. And the relations are of two sorts. First, we have braid relations. We have quadratic relations. So braid relations are as follows: Ti Tj is equal to Tj Ti if I minus j is greater than 1. Ti Tj Ti is equal to Tj Ti Tj if I minus j is equal to 1. And we get quadratic relations Ti minus q Ti plus q inverse equal to 0. I will maybe need notation for Hecke algebra. So what notation? I just denote it by Hn. We will not have Hecke algebras for types other than 8, so I just write the number, and I prefer write n, despite the fact that the number of generators are n-1. Why I'm and the theorem which I now claim that there is a map okay. There is a map from the Hecke algebra to endomorphisms of the represent as UQ of SLN model of the tensor product of the evaluation representation. No, of the standard first fundamental representation. And there is also part B of the theorem, which I will state in a minute. But before, I want to make the clear. I want to make part A clear. So how this map goes? Each generator Ti goes to R matrix which correspond to two I and I plus 1 sides. From this property, okay, maybe I should write. Okay, I left some place for the part B, but okay. How the map is defined? We have the map Ti goes to I plus 1 R tilde. As we stated, R tilde commutes with UQSLN. R tilde satisfied braid relation. This is the most non-trivial braid relations, and of course, if R tilde corresponds to factors which are not neighbor, where I minus j is greater than 1, as here, then correspond to R tilde's compute. And for quadratic relations, it says that the spectrum of R tilde is contained that R tilde has two eigenvalues, q and minus q inverse. And R tilde has a block structure. It consists of blocks 1 by 1, which is just by q, and blocks 2 by 2, which are like this. And it is easy to see that this matrix, so this matrix has one eigenvalue q, and this matrix has two eigenvalues, q and minus q inverse. Because you see its trace is exactly q minus q inverse, and its determinant is minus 1. So it has two eigenvalues, q and minus q inverse. So each I tilde has this. Okay, maybe hence we have intertwiner, intertwine. Property, we have braid relations, and last eigenvalues of R tilde are just q and minus q inverse. So everything's okay. So do you see my screen now?
У меня почему-то экран
Yes.
завис.
Меня тоже зависало, но сейчас видно.
It's strange that you see something because my Zoom said that you shouldn't, but okay. And what's going on now?
Definition of the algebra.
So theorem, proof of part A.
Видно.
Maybe you see my pointer to see. Okay. Please ask me if I should repeat something. We are starting slow, and because I want we change it. We have new topic, and this topic should, at least at the beginning, should be simpler than anything else. So ask me questions and so on. So are there any questions about proof of theorem of part A? Okay. If no questions, let me say about part B states that this map is surjective for let me state it correct, for q not equal root of unity. And I will not prove this. This is, proof of this fact requires some care, but instead I say the following: that for q generic, for generic Q, we have this fact because we have the surjectivity for Q equal 1. And if this we get the full centralizer for some special Q, then we should get it for generic Q. And the word generic is in algebraic sense. So for example, we get it for all transcendental Q. So for generic Q, this follows from
Но отображение не инъективно.
the map is in general not injective, of course. Yeah, but you know, for symmetric groups the same is it's not injective in general. Okay. Oh. We know the difficulty, the problem to map to be injective in symmetric group. So in this decomposition, we get a diagram which has no more than n rows. So if is in capitals greater than in small, then there are representation of this of the corresponding symmetric group which do not appear here. So this map is not injective.
Yeah, true.
Where am I? I'm in the proof. Okay, for generic Q follows from Q equal 1. And of course, for root of unity, in order to prove that true not for root of unity, it requires some more care about representation, about structures, Hecke algebras, and this I for generic. Okay. You know, our course is about affine quantum groups, so I will go to affine setting in a minute. But before, let me state just a bit in this not affine setting and say and introduce a few notions. So again, for generic Q, and actually no, for Q not root of unity. For generic Q, the affine Hecke algebra Hn is isomorphic to the group algebra of Sn. In particular, it has the same representation theory. So the group algebra of Sn is a direct sum of partitions lambda of n boxes of matrices of some size. How to denote the size? I don't know. Okay, and the morphisms of R lambda. And a chain has the same structure, so but it has the same set. How to say, the representation of the Hecke algebra also labeled by partitions, and they have the same dimensions. For example, it has two one-dimensional representations. Which correspond to symmetric and anti-symmetric representations. No, let me call them. So we have symmetric. So in terms of that it will symmetric and anti-symmetric, in terms of the representation, it will be trivial and sign. So trivial, it means that it is given by the formula that any Ti goes to Q. So any ti should go to some number in the trivial representation. And due to quadratic relations, there are actually two choices. They could go to q or minus q inverse. And if a q goes to equal to 1, of course, this is trivial, and sign representations is given by ti goes to minus q inverse. I don't know. Is it clear that it is impossible that some ti's goes to q and some goes to minus q inverse? That all ti's should go to the same number.
For me, yes.
Maybe you can explain to everybody.
So we should look at braid relation. So it is homogeneous. So it will be something quite bad if we send one t to q and the other one to minus q
Yes,
minus
exactly.
1.
Exactly. So for connected root systems like a minus 1, this braid relation tells us. So we have to, okay, two representations. And we can find, okay, more algebraically, we can find the corresponding elements which correspond to this endomorphism into the Hecke algebra. So we have symmetrizer, Q symmetrizer, and Q anti-symmetrizer. And Q symmetrizer is the sum of a W which belongs to in our case Sn Q in power of W TW, and here should be some factorial 1 over n factorial plus the following for, and here should be formula similar. So 1 n minus factorial sum of a W which belongs to Sn minus Q in power minus L of W TW. I actually, so maybe I forgot my to make one remark in order to introduce notation which I used here. Let me give it now. Remark exists surjective map from the braid group of Sn to the Hecke algebra. Indeed, for braid group, the only thing which we had is a braid relation. And in Hecke algebra, we have additional quadratic relation. So there is a such map. Maybe to be more honest, I should write here group algebra. So as well as a wide group is a quotient of the braid group by some relations, and Hecke algebra is also the quotient. And let me recall that for any W in the while group, we have element TW in the braid group. We take W, we take its reduced decomposition, K takes the product of the corresponding generators. So we get the elements TW in the Hecke algebra. So here W is a W is a sum. But actually, this is quite general remark. And this is what's going on here. So in order to take symmetrizer, I take all permutations and sum of them, and then divide over factorial. And in the Q case, the situation is the same, but here I should add additionally Q in power length of the W. And for antisymmetrizer, I take permutations, sum them with signs, and also divide over factorial. And this maybe I should state some properties in order to have the statements of the properties.
Так у меня вопрос есть. Вот тут написано n плюс квадратных скобках и n минус. Это что такое?
Good question. I was interested if somebody will ask. The same should explain. So we have there are different notations for Q numbers. Okay, let me arrange some space here. I don't know where. Okay, where? Here. So so one notation for Q number is that K is a Q in power K minus Q in power minus K over Q minus Q inverse. When I use notation with plus, it means that I take the following. So it is a Q number, but now it is a polynomial in Q. So it differs by ordinary Q number by Q in power K. And similarly for minus. So here we have summation of the positive powers of Q. So in order to somehow take the average, we divide over some positive number of powers of Q. So this is a factorial, which is a product of the plus numbers. Here we have a summation with the negative powers of Q. So in order to take the average, we divide over some of the negative powers of Q, which is a product of the, which is a factorial, in other words, product of the minus Q numbers. This notation which I used but do not introduce. Thank you for the question. Maybe there are other questions. Okay, if no, then let me state the proposition with the properties of these two elements. I should use some notation for them. Okay, the symmetrizer, let me denote them. As a symmetrizers, you will be Sn plus and you will be S minus n, anti-symmetrizer. So, and the property is the following, that if we have any Ti multiplied by Sn plus, it will be Q Sn plus. This A and B. This is one, and then, and Sn plus is a projector. And B will be for Sn minus. Minus Q inverse, and projector property will be the same. So these operators are project. If we have some representation of the affine Hicke algebra, then these operators are projectors to the symmetric part, symmetric submodule for the Hecke algebra, or antisymmetric. Yeah. In terms of the Hecke algebra itself, they are just the corresponding element corresponding to matrix units. The elements which correspond to one-dimensional representation. Okay. Other more questions?
I have a question. When you define the symmetry, the definition of capital N, if capital N needs some condition, because the n factorial maybe can be 0, so by
I
your
assume Q is
definition
generic.
about generic
Q.
maybe is not a root of unity of 2n or
Not root of unity is, I mean, not root of unity is sufficient, of course. I said generic, but if you assume Q is not root of unity, it is sufficient. We can assume that Q is not even weaker conditions, that Q is not Q is not n and minus 1 and so on root of unity. So then n factorial defines.
Okay. Oh, I understand. Oh, yes.
Generic is safe.
Yes, thank you.
This is a root of unity issue, which actually reason why everywhere should be reasons here, but and I assume Q is generic just for simplicity. Okay. If there is no more questions, then let's proceed to affine set. So we have okay. I'm struggling a bit with conventions. Below we had only type A, and here we also have only type A. I will write that we have Q of SLN, but at some point we have Q of SLN. It has evaluation representation, Cn, which have the basis, say E1 and so on, En. Now we take evaluation representation which is with formal parameter which I denote by y. So let me write this in words. So this evaluation representation with formal parameter. So I'm in the topic about affine dimensional representation, we put this y equal to just number, and there exists analog of this Schur-Weyl duality in affine setting where these parameters are numbers. It's okay, but this requires. I mean, this related, but a bit different story, and I pick to talk about the story with formal parameters for maybe because I know it better. Maybe it has some advantages for me. anyway, so this is now infinite dimensional representation. I will denote it. I will consider this space as a space with the basis ei, where I is the integers, where and they how to say, they are periodic. So ei, if we shift index by n, then we multiply by some y. In this case, y is inverse. Yes. So this is the definition of the space, and now we have to define an action, and the action of the algebra is defined by these formulas. And I put as a problem the fact that this is a representation of UQSL. Let me give a remark that here I changed some of my previous conventions. Maybe it is not. This is not very important, and maybe this is not clear for the from the first glance, but how. But okay, this was important for me when I tried to check something. So I say this. So how, for example, EIX. Now E1, it's only non-trivial term. It maps the first basis element to the second, to E2. We are maybe more used to call this to be F1, for example. So I changed. So now I changed the order of the basic elements. So now my first basic element, if I reorder them, en-1 and so on, E1, then E1, this generator will have this matrix. So in order to write a standard E generators to be upper triangular matrix, we have to change order of the generators. And this is done here. And all this I did in order to have E to make E increase the index. Because these will be annihilating operators, and it is they are increase the index of the generator. This is standard convention, conformal field theory, and corresponding similar constructions to which we will come, maybe not today, but next day. Okay, this is sorry for the long, maybe not clear explanation. The fact that this representation, this I left as a problem, does not, how to say, doesn't follow immediately from some facts which we knew, which we already stated, at least. We knew that there is a corresponding representation of the not affine ordinary SLN. But in order to state that this is some sort of evaluation representation of the affine SLN, we have to find evaluation homomorphism from the affine quantum group, affine quantum SLN to SLN. And in this, it exists for quantum affine SLN, but it's not trivial. And as we stated, this is a property of type A for D4 and for any other type which is different from A. There is no evaluation homomorphism. But anyways, this is quite easy to check. Maybe one more formula which I find, which a bit clarify what's going on, it will be formula for E0. So what E0 do? Let's look. E0, it maps basic element En 2 en plus 1, which is by our convention y times e1. So in our ordering of the basic elements, E0 is the following matrix, which maps the first basic element to last one with the y. So it is this matrix. The only non-zero element is this y. This should resemble, of course, affine root. Okay. No questions. Let me give one more remark. That on this on the vectors on the space representation space which we consider now, Cn y plus minus 1, we have an action of course we now have action of the quantum group Q SLN SLN hat, but actually we already have one operator which commutes with this UQ of SLN. Is it clear what is who is it? Who commutes with UQ of SLN? It is y. Operator y shift all indexes by n. But all these formulas, if we shift everything by n, it doesn't. All this equivalence mod n will survive. All this plus one, minus one will commute with shift by n, and so on. So in this case, even for one space, we have one operator which commutes with fine quantum group. And the question, of course, natural. Who else commutes? So, what is the endomorphism of UQ SLN hat of and now we can take Cn tensor y plus minus and tensor power. This is the formula. So I write it in blue color. I will use the following identification. So this tensor power Cn I will write it as a Cn tensor power n, and all y's I will write with indices. So this is y which for first factor, and so on. This is y for nth factor. This is a little bit more convenient for me, and this will resemble the answer. Are there any questions? Okay. If no, then let me state the title of the topic, and which of course the natural guess for the answer. Affine Hecke algebra.
Misha, now I have a question. Why it is a natural guess? So I understand that people who work in this area for maybe 10, 20 years or maybe 5 years, so this is a natural guess. But how can I, for example, understand that we can guess that it is an affine Hecke algebra? What it is not double affine? Why it is not degenerate affine, degenerate double affine?
I'm not sure that actually I have a good answer, but for your candidate, I think I can. Why it should be degenerate? Even for not affine case, we have not degenerate, but standard Hecke algebra, not degenerate. We had, you see, we had quadratic relation. So here, we had not degenerate and not affine case. So why it should be degenerate in affine case? Double and about double the same. We take only one affinization. So for centralizer, we also expect to have one affinization. If you start from the double affine quantum group, then it is, of course, it is natural to expect there is a somehow double affine Hecke algebra which commutes.
So the logic is pretty simple here.
Yeah, I think yes. So this is the first candidate. So we take affinization from one part. We ask for affinization of the second.
Thank you.
Okay, definition. And first definition is the following. So we have a affine braid. So affine and actually extended braid group action is a quotient of a braid or the group algebra of braid group by the quadratic relations Ti minus Q equal to 0. So we assume that we have braid relations and yes, we assume that we have braid relations and quadratic relations. Let me recall that this word extended means that we can add some external automorphism to the play. In terms of generators and relations, so more precisely, it will we have generators T0, Tr, and also some tau from the group omega, the group which differs of braid group from extended braid group to the ordinary braid group, which subject of the braid relations B is quadratic relations, and C is how the tau x on t. I will mainly use another presentation, so this is why I'm not going to many details in here. This is a braid presentation of the affine Hickey algebra, or if you want, Cox representation.
Misha, sorry, you mean braid relations on a cylinder or just so for T0 and TR or only for T1 and TR?
No, I put here T0, so T0 is involved in braid relations.
Okay.
So we have some Drinking diagram, which could affine Coxeter affine Cartan matrix. We read from the braid relations in the cylinder. Now, let me recall you that I'll write here surname. This Coxeter type. And another definition, which could be called loop presentation, or it's called Bernstein presentation. I'm not sure how it's written. I don't know, maybe loop presentation. And let me state it only in case which we need. So it will be for GLN. So affine Hickey algebra H N E E is generated by T1 Tn minus 1 and then Y1 plus minus Yn plus minus, which are subject of the following relations. So first of all, T1 Tn generate Hn. Standard Hickey algebra. So it means that so here we actually have again braid and quadratic. Relations. Second B, all y's commute. Yi yj is equal to yj yi. And C states the following, that Ti yj equal to yj Ti if j not equal I and not equal to I plus 1, and Ti yi Ti is equal to yi plus 1. So why it should be called like a loop presentation? So we have maybe I can't say it clear. What should this should resemble the following? So we know that recall remark to recall that even on the levels of affine while group, we have we have its definition, which is a Coxter. But on the other hand, we have its realization as a semi-direct product of the finite while group and translations, which correspond to weights. And this second presentation resembles this realization. So instead of W, we have the finite while Hecke algebra Hn, and instead of the translations, we have this wise. The fact that we have two realization is this new, what's new we have in a affine world. And I think that the fact that the non-trivial theorem is an isomorphism between these two presentations. I can write it as a theorem which is not precise here because I didn't give you Coxter definition for GLN case. But anyways, this definition can be done, and this indeed theorem that these two presentations are equivalent. Or maybe isomorphic. Questions? No? The fact that we have translations of affine while group this fact was used actively when we constructed Drinford's realization of the affine quantum group. And now we again actually come to the same phenomena. We have big commutative subgroup in the affine while group, but somehow from the different angle, different application of the same actually. Okay. Okay, if there's no question, then we can now go to our original question and define the action of the affine affine Hecke algebra on the our representation. So recall that our representation is Cn tensor n y1 we already have this y's which commutes and so on. The only thing which remains is to find t's, and we can find them similar to the situation which we had in the finite dimensional case. We can try to find them from the R matrix. Let me recall the formula which we had here. So this is a formula for R, if you want tilde. because now I change the order, I change it is important for here. Now I define the tilde. I change the order here. So maybe I should try this. So we have new another order. And this operator R tilde acts on the original Cn. But now, if we want so action of T on this how to write it to make it clear. So Ti should acting on some tensor product of two vectors, say E. So Ti action Ti depends on two consecutive factors, i's and i+1. So it is sufficient to define T in case of n equal 2. And for n equal 2, okay, let me do the following. Let me first write the formula and then I'll explain. Ti goes to the form. And just to state the theorem which we go on that theorem that we have a map from the affine wave group to the endomorphisms of this vector space. Over UQ SLN. And the map is defined by these formulas. Ti goes to what I wrote and yi goes to y. Okay, so this theorem which I'm trying to explain, maybe not even explain, this theorem requires some checks which I don't have time to do now. Actually, I want to finish soon because, as I said, there is a school now just about to start, and maybe suggest to. I personally, I want to go, and I don't want to avoid. If somebody else wants to go, I don't want to to do something convenient for him, to make parallel sessions, my lecture from the school. But anyway, I want to explain the meaning of this formula. What is SIY? There is one operator here. SIY is a permutation which acts on y's and do not act on the vector spaces. So we have, so SIY is this operator permutes y's. So similar, we can define SI. We can define SIE, and this operator will permute basically. We can define a full permutation SY, which will permute our factors. I say E with any factor. Okay, let me do maybe some check or some oh, yes, maybe I should do one more calculation as an example. Assume that n is equal to 2, which is actually sufficient to not understand meaning of these t's. And we want to act on t by some e, I don't know, EH tensor EG, where H and G from 1 to n. Then this H and G do not contain y's. So this will give us 0. So there's no such factor. And the only thing we get is our matrix. So it will be R tilde of H tensor EG. Now, if the condition is, if for example now I take E H plus n tensor EG and want to act by T here, then what I do, I write this as T y1 EH tensor EG. So let me recall that my notations for E basis, we have periodicity like this. So if we add by n, then we get extra y. Then we have to recommute this t with this E1. With this y1. For this we had the relation, so this should be equal to y2 t1 EH t1 inverse tensor EG.
I have a question. Which y should we add if there is a basis element EH plus n? Why is it y1?
I assume that H and G from 1 to n. Here and also here.
Does it follow from the notation?
This written here. So I keep this assumption on the second.
I mean, why isn't it like something? Why isn't it y2 times the same thing?
Y1 acts on the first factor, y2 on the second.
Okay.
So what I'm trying to explain that for any tensor, we have two indices of n equal to, and if both of them belongs to fundamental alcove, if you want, they both from 1 to n, then this T is just finite R matrix. But if not, then we have some extra y's, and we have to recommute T with extra y's, and then X by finite dimensional R matrix. So this is a combination of the relations in the affine Hickey algebra and finite dimensional R matrix. Let me finish the computation at least a bit. So this T1 inverse, so this is fine dimensional matrix inverse of it. If you don't want to have inverse of matrix, you can use quadratic relation and write that this is T1 minus Q inverse applied to EH over G. So this is Y2. So, and we get our fine dimensional matrix minus constant. And you remember this fine dimensional matrix is either it can multiply by something or permute this factor. So as a result, we can get again EH tensor EG or EG tensor EH, and then we apply Y2. So the second factor will be added by n. So here we can get either EH tensor EG plus n or EG tensor EH plus. Arjanya, more questions? So I'm trying to explain that this actually almost the only thing which we can do. So if we take or if we take indices of our basic elements from 1 to n, then the only thing which we can do is finite dimensional R matrix. And if they're not from this range, then affine Hicke algebra relations says what should we do? We should recompute T and then apply finite dimensional R matrix. And this is just the formula. Also, this is long word for recompute. Okay. Let me. So this main theorem of this topic, and clearly we didn't come to semi-infinite construction today, so it will be topic of the next lecture, and I think it's okay. It's better to talk entire lecture about this. But before this, maybe I want to give one remark, which is, I mean, you can ask, okay, this is a formal, but naively we should expect to have some affiner matrix. We know that for two representations, to tensor product of two representations, we know what commutes. Affiner, the matrix commutes. So we have a universal matrix for affine quantum group. We can compute this evaluation parameter, and also, and actually we did it, and we can find formula, and I can find. Okay, let me for speed find formula in my notes for this R matrix. This is it. Of course, you can. I mean, this is for SL2, but that is not important. And so the question is, where is this matrix? Why we should invent something again? And the answer is the following. We the affine R matrix okay, let me write it here, RA. So our RA say, the affine R matrix, it is it should permute this y's. So we so affine R matrix, it can no R tilde if you want. It acts from v tensor v to v tensor v, and from with the same coproduct. But now here we have y1 and y2 which acts on the first factor, and here we permuted them. They should act on the different factors. So affine R tilde should satisfy relation. And this is this relation differs from relations on T. And you can ask, what is can we correct this? And the answer is yes. So we can take T plus C x to T by some number and compute the difference. Now T1, as we wrote T1, so this we will get C times y1 over y2. Then if we move T1 through y1, we get plus y2 T1 I inverse minus T1. And T1 inverse minus T1 is something like Q minus Q inverse. So we get for C formula. This is Q minus Q inverse y2 y1 over y2. And you can see this formula actually here. So if you take so what I'm saying that the affine R matrix is not T generator in the affine Hicke algebra, but it is some sense another generator if you assume some denominators. So T plus Q minus Q inverse y2 y1 minus y2 is affine R matrix. But from the formula from affine R matrix, of course, it's not clear that we have some affine Hicke algebra, so I do not claim that well, this is the way to. For finite case, we just look to the Hicke algebra, to the affine dimensional matrix, and look at its Hicke relations. Affine case, logically different. Anyway, these remarks not very prepared. Let me stop.
Сейчас, а вот это вот T, это...
This T is T1, which lives in Hicke algebra. Как бы проблема, I mean, the problem which I resolve is that I define some operator T, and it is natural to have this to relate it to the affine matrix. Because we already have some operator, some natural operator which computes in some sense with the quantum groups or what are, and it computes with quantum groups, so it should belong to affine Hicke algebra, because we said this is a map and it should be subjective in some sense, of course. And now in this computation, I'm trying to explain you why. Okay, if no more questions, let me stop and everybody can freely go to listening exif.